so vibrant, so many people doing fascinating things. So I hope I'm able to keep your attention for 45 minutes. But in any case, thank you, Katya, and thank you all. My pleasure to be here. So I'm in Austin, Texas, and you know, one of the strange perks of this weird year is how easy it's becoming now to talk to a lot of people all over the world at the same time, early in the morning. So it's very happy to do it. I am going to give you a talk on the automated reasoning system, Imandra, that we've been building for, gosh, 7 years now, 6, 7 years. It's crazy. I mean, we started in a way thinking about it long before that, but I'm going to do it in a way that I've started to really like giving talks in the COVID era, and that is no slides. So I want to do everything with demos and with showing you our documentation. Forces us to keep stuff in good shape and make it usable and have enough information and so on. So hopefully this works. Let me start by just sharing my screen. Let's do a full desktop share. Okay, let me try to make these things the right size first. Can you read this? So I'll do some stuff in the Imandra command line, top level. But tell me, how is that font size?
Good for me. How is everyone? Sounds good. Looks good.
Good.
And what about this website?
A little bit small if you want us to read it.
Okay.
Depending how, yeah, that's probably now much better.
Second. What about that?
That's really perfect.
Okay, excellent. So let me just start with some background. And I'm a Texan, but I ended up, like some of my great mentors, 2 Texans, Boyer and Moore. I ended up, through them in a way, going to Edinburgh. And well, actually, even before that, so I was an undergraduate in Texas, worked with what's called the Boyer and Moore theorem prover. So you'll see there's big influences Boyer and Moore in what we do in Imandra. And one of the big philosophies of Boyer and Moore is, first of all, your logic should be based on an executable programming language. That's number one. And number two, you should exploit, in a sense, the inherent operational semantics of this programming language and, you know, the knowledge you have about the very restricted ways you're able to admit functions and define new data types. You should exploit that to make things like induction very automatic. And obviously, you know, when we're dealing with a full feature programming language, we're not going to end up with something that's a decision procedure for everything, you know, every query you can pose in the language, but we can go a long way. And that's one of the big ideas of Boyer and Moore. So I sort of grew up in a way, a part of this Boyer and Moore community, what's now called ACL2, but previously was called QThumb, an earlier version of the Boyer and Moore improver, and Thumb, and it goes back a long time. And then I moved to Holland, did a master's there, moved to Edinburgh, and did my PhD with Paul Jackson on decision procedures, in particular nonlinear arithmetic decision procedures in SMT. So did that with Paul and Leonardo de Mora at Microsoft Research, and the big focus, at least for my PhD, was adding what are called nonlinear real decision procedures, real close field decision procedures to SMT, and in particular to the SMT solver Z3. And in doing that, you know, sort of, oh, so by the way, the ACL2 Boyer Moore, that's based on Lisp. So the logic is, in a sense, a sort of variant of pure Lisp, you know, Lisp without side effects, but first order. So you don't have an ACL2, actually until very recently with some new add-ons, you don't have things like maps or folds. It's the recursions in a sense are explicit in your function definitions. And so in Edinburgh, as you can imagine, with Paul, Paul had done his PhD on New Perl. If you're familiar with New Perl, one of the sort of early actually US-based out of Cornell, dependently typed proof assistants, going back to the 80s at least. And New Perl was, like Edinburgh LCF and subsequent provers based on ML. And so I think to this day, even one of the main New Perl distributions still has an early ML there that's written in Lisp as part of its whole infrastructure that you install, which is archaeologically fascinating. But I was then being exposed to types and fought in a way tooth and nail when you come from the Lisp world. A lot of the, even Henley Milner, sort of lightweight type systems seem very restrictive. But over time, eventually, I made my way down as a postdoc with Larry Paulson in Cambridge. And Larry, of course, is a big ML guy. And in any case, I drank the Kool-Aid eventually and realized, sort of big personal awakening how amazing types are for various reasons. And, was brought, let's say, to the light, at least at the Henley Milner level of an ML. And with Larry, one of the big things was actually a joint Cambridge-Edinburgh EPSRC grant. One of the big things we were doing was developing new nonlinear decision procedures. In this case, decision procedures or even semi-decision procedures that could handle transcendental functions. And we ended up developing some infrastructure for that for SMT, things dealing like sine and cosine, tan, and so on, computable transcendental functions and constants, and also implemented this in a prover called Metatarski, which may be something that's useful for the work many of you are doing in analyzing neural networks, especially if you have activation functions beyond ReLU. But in any case so the influence of types became quite pervasive and sort of moved over more to the Isabelle Hall world. And I had done a bit of Coq also, some number theory in Coq previously, and when I was in Holland. A lot of that was in a sort of constructive context. But in any case, these ideas were germinating of wanting something that I think of as sort of a hybrid between a US, very Texan kind of prover, Boyer-Moore style, highly automated, based on a real-world programming language, together with something that's, but also untyped, together with something that is much more common in Europe, let's say, which is a Hall or Isabelle Hall or even dependently typed based system like a Coq or an Agda. And we started thinking, how could we bring these together? Because there is if you've never used a Boyer-Moore prover and you just come from the sort of modern proof assistant HOL style, et cetera, Coq, Agda style world, there is such a shock, I think, when you start to deal with the automation that you have in a Boyer-Moore world. It's very different. And in any case, so, as we're thinking of these ideas, my best friend from undergraduate, this guy here, Dennis, he was my undergrad roommate. And when I was in Cambridge, he had, at that point, made his way to London, and he was head of what's called the Central Risk Trading Desk at Deutsche Bank in London. And there, let's say something like 25 developers working with him, developing very complex trading algorithms and 10,000 plus line MATLAB brains sort of thing. And always worried, is somebody going to commit a line of code that causes the system to violate a regulation, to do something fundamentally unsound that would be bad for the bank, bad for the markets. And there was a growing realization that these trading algorithms were just becoming far too complex for classical, let's say, pre-formal regulatory techniques, but there was nothing at that point really formalized in regulation for finance for any sort of rigorous enforcement of the analysis of algorithms. So we realized there was a big opportunity there, and a lot of the techniques that we had been developing, for instance, at Cambridge, one of the big focal points of what we were doing was working on, applying our techniques to autonomous vehicle correctness. So to things like collision avoidance kernels in drones, and actually took a leave from Cambridge and I went to Carnegie Mellon with Andre Platzer for a bit to work on this in the context of his Chimera system. And so a lot of this was in the air, basically, that, okay, we needed to lift SMT to really handle nonlinear functions, but also we need something that, SMT is great when it works, but when it doesn't, we need something more akin to a proof assistant where we can work interactively, but we need counterexamples in a sense just as much, maybe even more than we need proofs. And so all of these ideas were sort of germinating. And we then decided the best way to do this was to found a company and try to build the system ourselves. And so that's what we did. It was a crazy first year of me in a closet, basically in London, just trying to write the first version of Imandra. And then Dennis quit Deutsche the next year as we gained some funding. And anyways, I'll walk you through some of the process here. But now if I fast forward to modern day, Imandra has become really a full-featured theorem prover and proof assistant, very different from something like a Hall, but complementary to it. So I like to think of Imandra as, in a sense, being a reasoning engine for the mathematics that basically every proof assistant can agree on. So whether you're first order ACL2 dealing with combinatorial objects that you could construct, computable combinatorial objects that you could construct inductively, or your COC with in many ways a much richer foundational system with a constructivist bent. In a sense, what Imandra can do, both of these systems will agree on. So we're very much in this. From the Hall perspective, or from the COC perspective, we're in the sort of Boole world. What we deal with is really concrete, finite combinatorial objects. But because we're restricted in that way, we have a lot of freedom to actually reason classically, but to end up with results that are constructively valid. So I'll make that more precise. But in any case, everything I show you is function. I mean, something that's been produced by jointly by our incredible team. Now I feel so lucky to work with the people I get to work with. And let me just show you so we can sort of follow along. I'll show you a few things. So first of all, if you want to get started with Imandra, so what I'm going to talk to you about most is what we call Imandra core. This is really the core reasoning engine of Imandra. And you go to our website, go to the docs page, and you'll see a lot of documentation. So you can install Imandra. We have community versions and commercial versions. Really, you can install the community version and have full access to Imandra. For non-commercial use. We have you can install Imandra directly. You can use Imandra as a Docker image, and also we have Imandra available both online and locally as Jupyter notebooks. I'll show you some of that. And then you can walk through the documentation, and I'll show you a lot of this. And the documentation is interactive. So if I, for example, here, this documentation is actually all Jupyter notebooks. And so you're seeing the input and output. And at any point, you can click try this and get an Imandra instance in the browser and experiment with it. So, okay, well, that's loading. Let me jump into a concrete example to try to make this more tangible. And then at any point, by the way, if you have questions, just please interrupt. So, okay, at the lowest level, Imandra is a reasoning engine for OCaml. So we've taken a subset of OCaml, a pure subset, but higher order subset of OCaml, and we have given it a formal semantics, and then we have built a reasoning engine around that and integrated it together with the OCaml compiler and the OCaml runtime, and built a lot of infrastructure around that. So what I'm showing you here is lowest level, Imandra top level, and this looks in many ways just like a normal OCaml top level. So by the way, how many of you have experience with OCaml? Well, maybe what's a better way to ask this on Zoom? Does anyone have experience with OCaml?
I've used it a little bit, but not too much, to be honest.
Okay. Are you more Haskell or?
Yeah, I use like Haskell a lot. Yeah, rather than I've used a bit of ML as well, but I've not just standard ML. But yeah, mainly Haskell and ML rather than Camel.
Okay. Anybody else?
I worked with Cork for a long time, so OCaml is good for me.
Excellent. Okay, well, you know, as you all know, OCaml is very much in the ML family. Actually, the syntax is much closer to the original syntax of ML than standard ML is, which, you know, things like if you've seen the strange double semicolon goes back even before standard ML. But if you've seen Haskell, I mean, this is going to be, I think, natural to anybody doing any kind of modern functional programming. But the idea is, so now we have a top level, and first and foremost, we just think of Imandra as a programming language. So for example, you know, I might define a recursive function. So here's how you do it in Imandra and in OCaml. So let's define a list reverse function. So we would say, you know, let rec, that means I'm going to define a recursive function. I'm going to name it reverse, and I give it an argument x's, and I'm going to match x's with, so that's how we do pattern matching, or one of the ways. And then we write our patterns. So here's the empty list. So if I want to reverse a list, of course, the reverse of the empty list is empty. And if I now match against the pattern, which is a list with a head and a tail, then you know, our classical reverse, I will reverse the tail recursively and append that to the singleton list of the head, let's say. Okay, so now I've defined this function, and this is a polymorphic function. So again, this is the same typical output you would see in OCaml or for the analysis, I mean, the analogous thing in standard ML. And this is just a function, right? So we can compute with it. So by the way, in the Imandra top level, we try to do a lot to, so this is different than the normal OCaml top level. In normal OCaml top level, you wouldn't see this type, for example. So we try to do a lot to sort of modernize it. But yeah, basic idea, you know, I can just go compute with this function. This is a real function. Looks like OCaml, it is OCaml, great. But behind the scenes, because we're in Imandra, and in particular, we're in something called Imandra's logic mode, actually, when I defined this function, it was turned into a mathematical definition. We had to analyze it for admittance into our logic. And in particular, in Imandra, whenever you define a recursive function, you have to actually prove that that function is admissible. And what that means is that introducing that function into our logic would result in a conservative extension over your previous theory before you had admitted the function. Basically that if your previous theory couldn't prove a contradiction, once you admit this function, you can't prove a contradiction. Relative consistency. And we do that using ordinals. So I'm gonna show you what this looks like, but basically what the point here is, look, for many things, especially structural recursions where you don't need to give Imandra a hint about how to admit this function, this is just normal OCaml. And now we can actually go, so at any given time when you're working with Imandra, you have a current logical world. That current logical world involves all of the data types, all of the functions, all of the modules that have been defined, building on the ground zero Imandra theory, basically the theory that Imandra has when it boots. That's something that is evolving. So as you define more functions, your current logical world is changing. And at any given time, you can inspect that in the history. So here we see, you know, we've had one event so far in our session, and we can ask Imandra to tell us about that. And it's, I'm have verbosity turned to the max, so I'm going to show you lots of stuff. But basically, we see here, so IML is the name of our logic, Imandra modeling language. And we see now our function definition for rev, in a sense, translated into IML. That big difference here is that pattern matching has been compiled or has been expanded. And we have destructors like list.head and list.tail as part of that pattern matching expansion. And we can see lots of information about our function. So, the name of our function, here's the type, it's polymorphic, it's recursive, some metrics about the complexity of the function that actually play into how this function will work with induction. Crucially, this is very simple here because this function only has one argument, but whenever you define a recursive function in Imandra, one of the things that we do when we prove it terminating is we determine something called a measured subset of its arguments. And so this is in general a subset, could be a strict subset of the arguments, and these are the arguments that are actually used in the termination proof. So intuitively, these are the arguments that are going to be destructed, or in effect, some function of them is going to be smaller in some ordinal valued measure when we do recursive calls. And that means basically these are very important arguments later for when we go and do induction, because as I'll show you, the way we do induction is we basically mine the termination proofs of the recursive functions, in a sense dualize them, and then construct an induction scheme that is tailored to a conjecture by taking into account all of the recursions that the recursive functions involved in the conjecture do, right? By analyzing and exploiting their recursion schemes. So then we'll see we have proofs, and we're looking here at the actual proof involved in the termination. And you'll notice here that this involves ordinals. Okay. Now we see we have this. Oh, and by the way, let me just show you also. History full. Let me show you what this looks like from our ground zero theory. And so here, when Imandra boots, sort of like a Haskell, it has a prelude called prelude.iml. And effectively, we can go back and trace the entire booting process of building our logical theory from scratch. And one of the most important first things that happens is the definition of ordinals. So this ordinal module, and I'll walk you through that. And one of the key axioms of Imandra's logic is actually the well-foundedness of ordinal less than, and we build on that for our definitional principle. Let's see, natural numbers, lists, et cetera, et cetera. Okay, and that brings us all the way to our reverse function. So now that we have reverse, and again, this is a function that we can just compute with, but we can also reason about it. So again, one of our biggest goals has been to, actually, I don't think I've said this explicitly so far, so let me say, one of our biggest goals with building Imandra, founding the company, et cetera, has been to really take modern formal verification and turn it into something that an engineer can use who has no background in formal verification. Basically make it an engineering tool that is easy, where people don't need to understand how it works, and it can just become a part of their daily life. And to do that, one of the big design decisions we made very early was to put counterexamples in bounded verification, put that in a sense on the same footing as what we hold classically very dear, which is real formal proof, unbounded inductive proof, which is typical for what we need to do for an infinite state system, for example. But over time, we've really, with applying Imandra in industry, we've really learned that, first of all, most of the time, the systems that people want to analyze are not correct. Most of the times they have flaws, often very subtle flaws, and the construction of counterexamples is really paramount. So we're not going to be able to prove most of the time the theorems we think are true because they're not true. And we need very robust automated techniques for finding those counterexamples, and then for helping people extrapolate from those counterexamples and exploit them to ultimately fix and prove the theorem correct. So that's a big thing, is that we see counterexamples as in many ways as important, and in some ways even more important than proofs. And then on top of that, we want to have, and it's connected, but we want to have bounded verification. Something that's totally automated, requires really no expertise at all, to be available at any time, and basically to only to have a sort of philosophy where you only go to unbounded verification, which may require some expertise. You only make that leap if bounded verification has succeeded, if you have eliminated all counterexamples up to some bound, for example. So let me show you sort of the entry level of what that looks like. So in Imandra, we have a command called verify. And when we want to verify something, what we give is a lambda term. And what we're asking Imandra to do is to prove that this lambda term will always evaluate to true. So in OCaml and in Imandra, lambda is written fun. And so here we can say, verify fun x. And so you can read that really as verify for all x, because we want Imandra to verify for all inputs, in a sense, into this lambda, that lambda will evaluate to true. But verify for all x that, let's say rev x is not equal to 1, 2, 3. So totally silly thing, not true. And Imandra comes back and gives us a counterexample. So one thing to note is this counterexample was done modulo recursive function, also was done modulo arithmetic. I mean, very simple arithmetic, but these are real integers, so to say, arbitrary precision integers, backed up by a theory of arithmetic. And so when we do this, we're asking Imandra to prove a universal theorem. It comes back, gives us a counterexample, and that counterexample is first class. So what I mean by that is, and this again was a very important early design decision for us, whenever we do have a model in Imandra, that model is executable. Typically, it's written as a simulator for the system that's being designed, and we want counterexamples to our conjectures about that system to be accessible. We want them to be computable and directly runnable through the executable formal model that's in the same environment. And so that's why whenever we do compute a counterexample, we actually reflect that in the runtime. So you'll see this module CX, and it has a value called X. So this is how you see a module signature sort of interface printed in OCaml or in Imandra. And so that tells us there is a module here called CX, and it has a value called X in it. And if you look now, that is exactly our counterexample value. So whenever you do get a counterexample, by default, you get together with it a computable defined module called CX that you can directly interact with and use to interrogate your model. So this is a real OCaml value now. And so now we could say, for instance, we want to reverse cx.x, and we see that that's 1, 2, 3. So it really is a counterexample to this false conjecture. So that is one of the big ideas, is that you have first of all, your formal models are executable. They're high performance. They're OCaml. They can be directly compiled with the OCaml compiler and run, co-simulated with your production system, or even exported to be your production system, for example. So that's number one. Number two, you have integrated verification that really puts a lot of emphasis on counterexamples. And so I can point you to our IJCAR paper if you want to learn more about how this works. But basically, we have here what's called recursive function unrolling, but a fair strategy driven by unsat cores that is, in a sense, looking at the recursive functions involved in the conjecture. At any given time, in a sort of information ordering, we have a definition available of various ground instances of the recursive function. So bounded interpretations of the recursive functions involved that are ground. And basically, we block the paths to uninterpreted instances of those recursive functions. So we have this sort of growing lattice of interpretations of recursive functions. We are looking for counterexamples, and why can we do this? So fundamentally, because our functions are computable, right? We know they terminate. Then if there is a counterexample, we know a counterexample would result in a finite call graph, right? So because our conjectures themselves are executable, counterexample is corresponds to a finite call graph or execution trace of our counterexamples that evaluates to false. And so we, in a sense, can search this space of these call graphs that evaluate to false. And so that's what this sort of search over this information ordering is doing. And at any given time, then effectively, if we get a counterexample, we know it's real because we block all of the interpreted sublattices. But we may get a spurious proof that says, for our current interpretation, this conjecture is not valid. And what we have to do is look at that proof and see, did that proof of unsatisfiability involve any blocked paths? And if it did, then this is not a real proof, then we need to unblock a path. If it didn't, then we're done. And if it did involve a blocked path, we basically minimize the proof, look for an unsat core, and that points us to a path that should be unblocked, basically. So a part of the recursion that we need to go down. And this has to be done in a fair way. And so anyway, so that underlies what we call recursive function unrolling. That underlies how we do this search modulo recursive functions. And anyway, so now we have counterexample. Great, we see this thing is false. And that is a lot of what people do with Imandra. They have counterexamples and they then use them to repair their system and repair their conjectures. So, okay, let's do something a bit more interesting. Let's say that instead of something that's false, we try to prove something that's true. So now, for example, let's say we want to prove, first let's start with something that doesn't involve induction. So recursive, this is just very simple. Oh, oops, sorry. So verify in this case, if we don't ask Imandra to do induction by default, we can change this, but by default it won't. So by default, we're just doing bounded verification, which is typically good for engineering applications. But there's a lot we can do with bounded verification. I mean, here's something very simple. So, okay, that's obvious, and we don't need induction for it. But now let's say we want to prove something by induction. And so, for instance, we want to prove, let's do recursive x. For all x, recursive x equal to x. And this is something that is going to require induction. So by default, we're not doing induction. We didn't ask Imandra to do it. We asked Imandra to do this bounded verification. And so Imandra tells us, okay, I couldn't find any counterexample up to our bound. And you can configure this global bound here if you look at config. This is the default recursion and rolling depth, but you can change that. So, okay, so that is a nice result in the sense that we have now verified, as I was saying, the space of finite call graphs. Basically, we verified for a non-trivial space of possible executions of these functions. There is no counterexample, so that gives us some conviction that this property may be true. There is often a small model property with these models that I think this would be a very cool PhD project if somebody could ever crack this. But very often, if there is a counterexample, there's a small counterexample. And so even a bounded verification like this could, in some senses, be turned into a proof. But in this case, we just see this as, ultimately, this is a formal result of unknown. And first of all, let me just show you one thing useful for engineering applications. And that is, you can actually tell Imandra what you want here is a bounded model checking result up to a bound. So here, we're explicitly saying, I want this result to be verified up to this bound. And then that actually comes back, I mean, this is truly an interface, sort of thing, but this comes back with a green check mark. Instead of saying unknown verified up to 100, we're making our goal here explicit that we just want to verify this using bounded model checking up to this depth. And that's something now that, is a positive result. So that's useful if you want to put these as part of continuous integration or even as part of a safety case where you're very explicit about the fact that this verification is bounded. So there's a lot of support for basically, treating bounded results as being first class. And you can then ask Imandra actually to translate this result into a formal statement where you have bounds on the data types, for example, as part of your hypotheses. So if you want to use this in a bigger effort. But okay, So again, that's still bounded verification. So let's now go to real mathematical proof for the unbounded case. And that's where we start to get into induction. So what I'm going to do, just show you what this looks like. And another goal, and this goes back to Boyer and Moore, another goal for Imandra has always been to make the verification results understandable, especially when they involve things like induction. So we can ask Imandra to prove this, and you'll see, so great, comes back and says they're improved. We get a quick summary here that it actually did 2 inductions and had to use some recursive definitions. And I'm just going to quickly walk you through this, and then I'm going to show you a better way to do this that's more disciplined, and then tell you a bit about sort of background of how we automate induction. Okay, so here basically we asked Imandra to do this, and when we say auto, we're asking Imandra use our automated induction techniques, what's called our inductive waterfall. And so we start with this. Here's our goal, that reverse of x is equal to x. Imandra, core part of this inductive proof technique is a powerful simplifier that does conditional rewriting, does forward chaining, destructor elimination, a lot of things. And here, fundamentally, what it's realized is we can't simplify this anymore, so we have to try induction. And so we have integrated here, as we go, we have bounded verification involved, because if we do a speculative step like a generalization before induction, we want to filter those heuristic speculative steps by bounded verification to make sure we haven't overgeneralized, for example. But we see now, okay, we need to do induction. And so what Imandra does is it analyzes the recursive functions involved and what their instances are involved in the conjecture. And each of those, based upon the way they did recursion and based upon their termination proofs, they each will suggest an induction scheme. And in particular, this inner one, reverse x, suggests an induction scheme that is dual to the way that reverse does recursion, which is structural. And so we see that it suggests this recursion, which is really structural induction in this case. And then we go to apply it. And so this is a very simple induction. We are able to prove the base case by simplification. So crucially here, what happens is, and why there's so much automation, is we are speculatively opening up the recursive function bodies, paying attention to the fact that we're under an induction and we know what the inductive hypothesis is. And we are then trying to simplify these recursive function bodies towards being able to take advantage of the inductive hypothesis. And so that's what's going on. And so base case is easy here, but now we keep simplifying, and we then reach a point where we can't simplify anymore, but so effectively now what we're doing is we're saying, okay, we can't simplify this anymore, so probably we're going to need to do induction. So let's prepare our conjecture for induction. And so we then go through a number of steps, and one of the first ones is the elimination of destructors. And that gets back to the basic idea of, even in number theory, if you're trying to prove a conjecture about the natural numbers and you have subtraction involved, one of the sort of core tricks you learn very early is, oh, can I reformulate my conjecture so that it's involving addition instead? Because addition in progress tends to play much better with induction than subtraction does. And so, sort of high-level analogy here with destructors on data types. So in general, it's a lot easier to do induction if we, notice here that we have as a hypothesis the fact that x is non-nil. So that means x is actually equal to a cons, in this case, a cons of a head x1 and a tail x2. So we can eliminate the instances of these destructors like tail and head by just replacing x with x1 cons x2. And then we have now a much nicer looking conjecture for doing induction that involves x1 and x2 and doesn't have those destructors around anymore. And next we do something called cross-fertilization, which again is a lifting of a Boyer-Moore idea. But the idea is that, especially when you're trying to inductively prove an equality, often what you want to do is apply, use an equality in a way that may go against the grain for a simplification ordering. You may actually replace something simpler with something more complex, but that makes it better for induction. That's so-called cross-fertilization. And then you want to throw away that equality that you use because you want something stronger. You don't want to have that hypothesis around anymore. So we basically use this equality here and throw it away, so to say, and that gives us now this revised conjecture. And then the last big thing we want to do before induction is generalization. So we want to look, is there any way we can strengthen this conjecture? Because, in induction, what we have at our disposal are instances of what we're trying to prove. So we want to make what we're trying to prove as strong as possible, so that it, is hopefully inductive, so that instances of it are sufficient to prove it. And yes, we realize here we can generalize this common subterm on both sides of the equality, reverse x2. And so we do. And so then we finally end up with this conjecture. And if we read this, that's that the reverse of appending some value gen x1 with a singleton x1 is equal to x1 const onto the reverse. So that's a sort of one step here where this has been restricted to be a singleton. And now that's something that we also need to prove by induction. So now we recursively go through our whole waterfall process, analyze the recursions involved here. Here we recognize that it's best to do recursion following the definition of append. We do, and boom. Okay, so that's a nice example of a successful automated proof by induction. And let me just point you in our documentation to, if you want to learn more about how we automate induction, here, this has a lot about it. And this is this process I was just showing you, the so-called waterfall. And this idea goes back to Boyer-Moore. We've just lifted it to our typed higher order setting because they're in an untyped first order world. But the biggest workhorse is simplification. We have recursive function unrolling, looking for counterexamples to make sure we don't make missteps. And then these other processes I was showing you, these are all basically preparing things for induction, and then induction, and boom, this goes recursively. So, okay, so that's nice. It's always nice when something's automatic, but notice this involved multiple inductions, and this is a case where it worked, but this is working in general over an undecidable theory. You can do, arbitrary number theory here. So let me show you something that's more realistic about how we typically work. So let me go back. I'm going to undo. So UBT, this is undo back through. And so I'll undo back through. Actually, let me just undo. So let's get back in a world where we just have reverse. And now I'm going to do something called, actually, I'm going to do max induct. I'm going to put a limit on the number of inductions we can do in a proof. So this is a way we often work. And if I show you now, here, our current configuration, we see that we now have a max induction depth of 1. And the idea here is, in that proof that we just did, we had multiple inductions. But typically, if we restrict ourselves to have a single induction, then what this Imandra waterfall proof process will do, it will point us to useful lemmas. And that way, and instead of just having Imandra go and do a bunch of inductions, we can have Imandra guide us to very important simplification rules, for example, that could then help us develop a theory for reasoning about a collection of functions or data types that then makes other proofs easier, and they make subsequent proofs be provable by simplification alone. So let me now go back to what we were doing before. Now that I have told Imandra only to do a single induction, and instead of just saying verify, I'm going to use the keyword lemma, which effectively does the same process, but allows us to name the result and save it so that we can refer to it later. So now I'm going to say, let's try to prove a result we're going to call rev, and that will be this. So we're going to ask Imandra to prove this result. If we prove it, it's going to be called rev, and it has the same body as before, that reverse of x is equal to x. But now we've told Imandra you're only allowed to do one induction. So Imandra does the same process that we did before, but notice it ends up here with needing to do induction, and we've told Imandra, hey, you can't do that. maximum induction depth is 1. And so we end up with this result that we had tried to, or previously we had proved automatically by subinduction. And typically now what we do is we look at these results. So Imandra prints them out as a checkpoint saying, here's the main result you should look at. And that is the result that's stable under simplification before we need to do a subsequent induction. So we look at that typically, and we could go and try and prove that directly. So that's what Imandra did when it previously proved this result. But often what we do is we look at it and say, is there any stronger result that this suggests, something more general? And what we pay attention to most are the nestings of recursive functions. So here we see we have reverse and append nested. So, question I would immediately ask myself is, does that suggest anything? And if you think about it for a minute, it does. So let's say rev append. So now let's ask Imandra to prove this. And that is that the reverse of x append y is equal to the reverse of y appended to the reverse of x. And now I'm going to ask Imandra to prove this lemma. And if it's able to prove it, I'm going to ask Imandra to install this as a rewrite rule. So that's what that means. So we ask Imandra to do this. But again, note we have still our max induction depth restricted to 1. And so Imandra goes to prove this, and it's able to, it recognizes how to do induction, et cetera, proves the base case, gets to this inductive step, and then recognizes, oh, I need to do a subsequent induction. And what has it reduced it to? And it's reduced it to this. This is the key checkpoint. So if I had a max in depth of 2, Imandra would just prove this for me. But it's very nice to have a max in depth of 1, because now I see, oh, wait a second. Imandra doesn't know that append is associative. So that's what this is saying. We've got append, gen 2, gen 1 x, and again, gen 2, gen 1 x. So let's just teach Imandra that append is associative. So now let's go and do that. So I'll say append assoc x, y, z, and let's say that x append y append z is equal to x append y append z. Again, I'm going to say ask Imandra to prove this by induction and install it as a rewrite rule. And so that Imandra is able to prove with a single induction. Great. And if we go back now to our rev append, Imandra is able to prove that by a single induction. And notice it then makes use of our rewrite rule that append is associative. And we go back now to rev, and Imandra is able to prove that now by a single induction. And notice it used our rev append rule as a rewrite rule. So this is pretty indicative of when we're going to prove inductive theorems using Imandra, the process of how we work, and we use Imandra to guide us towards lemmas that then teach Imandra how to reason in a specific domain. Okay, so let me, by the way, does this end in 4 minutes? Should I?
I don't know. So I'm free. I'm interested. So we probably can afford another 10 minutes, 15.
Okay, perfect.
Tell us what we must know. Grant.
Right.
That's the main thing.
So, okay, so now let me try. So that's just a big picture, bounded and unbounded verification with counterexamples that are first class, all built on, executable programming language. Now let me show you, just before we end, some applications that may be relevant to you. So if we go to explore and let's do demo gallery. So if you go to demo gallery, you can see, just examples grouped by, in different ways. Let me show you a few that might be relevant. So for instance, here's a simple vehicle controller. So here's one where we're verifying correctness, safety properties of a simple autonomous vehicle controller. And that might be one that's nice to go through. And it shows sort of the big idea of, look, the way you approach this is your controller is going to be executable. It's going to be a function of a state, which is, for instance, all of the current, think of it as all of the current knowledge of the world and of itself that your controller has at a given time. And then the state responds to sensor readings. And so that's, or the controller rather, responds to sensor readings and updates the state accordingly. And again, this is all executable. Yes, actually, let me just load this just to show you what experimenting in Jupyter Notebooks looks like. And this kind of paradigm of building an executable, in a sense, an infinite state machine, but something that's where you just have a data type of a state and reasoning about it. This is typically how we do a lot of things. So here I'm defining a state for a vehicle controller, current wind speed, current Y position of the vehicle, accumulated velocity. Here's a little controller. So these are just interactive Jupyter Notebook cells. Here is a step function that basically takes a state and a wind sensor reading and evolves the state, crucially modifying the velocity by our controller. And then, when we want to prove safety properties about this, again, our logic is based on OCaml, so everything we write is executable. It's all functional programs. So, for example, what we want to do is we want to restrict ourselves to wind sensor readings that fall within a valid range. So what we're going to, the way we're modeling this is the wind sensor readings that we're going to get are actually deltas, telling us if the wind has slowed down by an integral unit or stayed the same or sped up. So this is a predicate that's using a list dot for all function. That so this becomes a predicate of a function which is a bunch of wind sensor readings, and when it comes to reasoning about the correctness of our system, we just use these computable predicates. Again, just like we would write a runtime verification check, for example. This is a computable predicate. We then can subject that to proof. So here's just like a little recursive fold function that takes the state of our system and a list of wind sensor readings, and it's going to fold over that by progressing the system with our step function. And now we can come to trying to prove properties of it. So, here's a nice example. If we start in a good state and we evolve the system responding to one sensor reading, then we end up in a good state. Here's our definition of what a good state is. This is just an executable function. It's a predicate, and here's what our theorem. So theorem means the same thing as lemma. We just use it typically for a bigger result, but it does the same thing. And so here's our theorem safety one, and we're asking Imandra to prove for all states and all single sensor readings or single sensor deltas, if our state is good and our delta has a valid value, then if we step our system and check it, then we'll end up with a good state. And so we ask Imandra to prove this, and great, it's able to prove that. And notice we make that into a rewrite rule. And so now, because we have that available as a rewrite rule, it makes it very easy to lift these things via induction. So here's our multi-step safety. If we start in a good state, simulate the controller with respect to an arbitrary sequence of sensor readings, then we still end up in a good state. And this is using that previous recursive predicate about a list of sensor readings, arbitrary length list being valid values. And now that is a property that we ultimately prove by induction, we see. And that used our safety property that we proved for in the step case. So this paradigm, of having complex physical systems, for example, having core logic of them modeled as an infinite state machine in Imandra that, has a state data type that has, in a sense, an infinite state space, right? It has arbitrary integers in it and so on. And having recursive functions involved in the simulation and in our correctness statements, that is very typical of how we work, because we're able to do induction over those things, so they don't need to be finite state. But if we have counterexamples, we can restrict those counterexamples to a bounded space of them, and that then allows us to get out nice counterexamples. So let me show you, for example, if we had defined a flawed version of this controller, and same process, but we tried to, so basically it's flawed because one of these coefficients is different, it's wrong. If we tried to prove a safety property here, this is one of the main theorems that if you go through this, you'll see we prove above that if we start in a good state, that we never veer more than 3 units off course of our desired trajectory, then this isn't true. And so Imandra is able to synthesize a counterexample. And so here we see if the wind is increasing in speed for 3 time steps, then actually this flawed version is incorrect. So in any case, that just to give you an idea of sort of how working with Imandra on these, more sort of real world systems, what that looks like. And let me show you now something that's very typical to what we do in finance. How Imandra is used. Yeah, let me show you just 2 things there. So this is one of the sort of pretty rare big applications of Imandra in finance that's fully public, that you can go through. And we have a CADE paper from a couple years ago called Formal Verification of Financial Algorithms that goes through this. But basically the idea here is when you are an investment bank like UBS, for example, typically you will run something like an exchange, what's called a dark pool, inside of your bank. And that is, a software system where people can submit orders, like buy and sell orders for a stock, and you will match those orders and have trades take place. And that's classically something that you would expect an exchange to do, like London Stock Exchange and so on. But what's happened over the past 20 years or so is that banks, with a big regulatory framework to make this legal, banks have realized there are a lot of advantages to crossing or trading these orders internally. First of all, a big bank may have clients who want to buy Microsoft. They may also have clients who want to sell Microsoft. It could make sense for them to just match those clients internally instead of going to a public exchange, because if they go to a public exchange, first of all, the intention of their clients is going to be public. Other people will see, what's happening, and they may want to keep their cards close. There's nothing inherently unethical about that. Number one. Number two, there's transaction fees. There's all sorts of, stuff that could incentivize you to try to match these orders internally. But of course, if you have less scrutiny, like you're less public, a lot of things can go wrong, and they classically have. So that was a big thing we set out to address when we founded the company, was bringing transparency to these very opaque trading systems, like a dark pool, and giving regulators and practitioners a way to analyze their algorithms for fairness properties, for example, that they were just so complex they couldn't do them by hand anymore. And so when you are a bank doing this, you in the US, you have to file a regulatory form called Form ATS with the regulator that explains how the logic of your system works. And this is, actually, let me show you quickly what this looks like. Do I have one here? Yes. So this is, a 28-page document written in legalese that is defining a very complex algorithm. So, here we see UBS ATS allows all order originators to use the following optional crossing restrictions. You can use something called pegged midpoint mode, et cetera, et cetera. Then this is one of the most interesting and most important from a fairness perspective aspects of the logic. What this is doing is this is basically saying how if you submit an order and that means you have an intention to trade, how should you be prioritized? And that's classically where a lot of unfairness in the markets has happened, because if you don't have a lot of scrutiny and you're a bad actor running one of these venues, you might decide to prioritize your friends over everybody else and give your friends the ability to front run or to trade and jump the queue unfairly before others and so on. And there's some fundamental fairness ideas like what's called price time priority. This is sort of something everyone can agree on, and that is if you submit an order to trade and you were there first and your order is more aggressive, meaning you're willing to pay more for a buy or accept less for a sell, then you should be given priority, right? That's price time priority. And there are many examples, though, where price time priority has been violated, especially in dark pools. So here's a very interesting example where these 3 paragraphs are actually defining some very complex logic about how orders should be prioritized at this dark pool. And the regulator approved it. Regulator said, yeah, this is fine. You guys can do this. And then it turned out UBS had issues, and very publicly they were fined $14.5 million by the SEC for issues of unfairness in the system. And this was early on when we founded the company. We saw this as an opportunity because this settlement these documents were made public. And so we built an interface to Imandra to make it easy to formalize this stuff. And so that's what you see here. Let me actually just run this whole thing. And basically, this is an executable formalization of that logic. And notice the market can be in a bunch of states. We have a feed of market data coming in. We have prices. We have all of these different order types that can trade. Orders can be buy, sell, or sell short orders. The orders can have what's called pegged prices, where you pay attention to a data feed of a price coming from a public exchange, and you peg to that. You're a function of that public price. Okay, and if we go all the way to, so you'll see, order has a lot of data. But again, this is OCaml, so we can actually run this. This is really a simulator for that venue, but we can then reason about it. And if we jump down, so these are a lot of complex functions that are implementing the logic expressed here about how orders are going to be priced. And if we jump down to the sort of main order priority function, so these are those 3 paragraphs that are describing, if you have a buy order, collection of buy orders, a collection of sell orders, how should those lists be sorted? And the idea there is the top eligible buy and the top eligible sell, those will be the ones that can trade with each other. So you want to, your goal is to be at the top so that you have the possibility to trade. But we want to make sure that that process of an order going to the top is fair, right? And so this has a core ranking function that takes a side of the book, like buy or sell, 2 orders, current market data, and decides if one order should be ranked higher than the other. And one of the most fundamental properties that you would expect of this logic is that a ranking function like this is transitive, right? If this ranking function says that order 1 should be ranked higher than order 2, and order 2 should be ranked higher than order 3, well, it better then also say order 1 should be ranked higher than order 3. And if you sort of eyeball this, you can maybe convince yourself that that's true, but it's very complex because this logic actually sets up a sort of competition between the orders that's first based on price. And it's not the real price. It's not just the price that the order has. It's something called priority price, which is a function also of the market and a function of what the kind of order, what order type the order has, and if its price is pegged. And anyway, so quickly you realize this is way more complex than you might think. And if we then go and ask Imandra that this, is this transitive? Is it always the case for all sides of the order book and all triples of orders, that if order 1's ranked higher than order 2, order 2's ranked higher than order 3, that always order 1 would be ranked higher than order 3. And Imandra comes back and says, no, that's not true. And here's a counterexample. And so just to show you, these counterexamples can get very complex. So here Imandra's actually synthesized all of the data we need. It said on the buy side, if we have order 1, which is a pegged midpoint order, which is market type of quantity 6, which is resident principal capacity, blah, blah, blah. And we have a pegged conditional indication order pegged to near. And we have another pegged conditional indication order pegged to near, which has a certain midpoint mode. I can find, where is it? Well, anyways, there's a bunch of complex things here. Okay, yeah, category C1, order attribute resident. Anyways, we now have these values that are synthesized for us, so we can actually compute with them. So again, these are now available to us in the CX module. And if we look, so one of the things we've done in this notebook, you can write custom printers that print your data types in nice ways. So now this is just showing us in a custom printer that makes a little HTML table. But now we can actually run Imandra on these values to see. So we can see that, okay, order 1 is ranked higher than order 2 with respect to these values. Order 2 is ranked higher than order 3, but actually order 1 is not ranked higher than order 3. And so now, because we have these complex counterexamples in the same environment as our executable formal model, everything's reflected, we can very quickly find these counterexamples, compute with them. We could start tracing these functions and see what path it's going down and so on. And because I know we have to end, let me leave you with the last thing, which may be interesting to you, which is Imandra for reasoning about various machine learned models. And again, the idea is the same. Basically, whether it's random forest or decision trees or neural networks, you just can translate your model into Imandra. So, here is an automatic result of an automatic translation of a random forest, for example. A bunch of trees, those are all Imandra function definitions. And then we have the combined random forest that just composes those. And then we can define data types of input and all of our normalization. Again, these are just OCaml functions, but because they're in Imandra's pure fragment, we can reason about them, but we have real numbers, we have arithmetic, recursive functions, and so on. And now we can compute with these things, but also we can query them. So here, for example, we've taken this random forest model, which is a classifier for skin lesions to see if something looks, should be classified as malignant or benign from a cancer diagnosis perspective. And we can ask Imandra, is there any input that would result in benign? And we'll get out an instance. So instance is dual to verify. Get out a model, dual to a counterexample. And we see yes. And then we can compute with this. And then we can go on and further verify. And finally, a last thing that may be useful for you is underlying Imandra is a technique we've developed called region decomposition, which basically lets us go and you can think about it as sort of hybrid between symbolic execution and predicate abstraction. But basically for a given abstraction, you can then get a description of all of the feasible behaviors of your system. In many ways, those sort of correspond to interesting lemmas about your system or invariants. And then you have this available as a data type that you can interact with, compute with. You can query, you can ask Imandra, show me all of the regions of the state space of this random forest that would result in benign using this abstraction, for example. And that typically allows you to learn a lot about your system, and we build a lot on top of that. So I could keep talking. I don't want to keep you guys. I know some of you need to go to sleep. So let me just stop here and see if there's any questions.
Thank you very much, Grant. That was a great talk. Everyone, please feel free to switch on your cameras and ask Grant the question. I will start while everyone is thinking. I'll start with the key question for us. Grant, if someone said, that's a fantastic system, I really want to use in my research project, what will be the first step? So I guess we could get a free version on the web.
Absolutely. Yeah, it's full featured. So if you go to, if you're on our website and you go to Docs, Imandra Core, and you go to Installation, and probably the easiest way is just to do this default installer, and you just copy and paste that, and it works on a Mac or Linux or Windows if you have Windows subsystem for Linux 2, I believe.
Okay, and how should we license the things that we create in Imandra?
I mean, that's really up to you. So for academic use, you can just use Imandra. And so something to know. We're cloud native. So basically what that means is what you're going to be installing is an Imandra client, which we have a VS Code interface with asynchronous, editing, kind of like Isabelle, JEdit. We have our top level that you saw in the command line. And then we also have Jupyter Notebooks, so you can use all of those. Those are all client side. Well, what's going to happen is when it comes to doing reasoning, you actually, whenever you boot up Imandra and log in on the client, we spin up in our cloud what we call a reasoning pod. And that is, Imandra cloud services that are going to be doing the reasoning for you. So it's seamless from your perspective. You don't see it. But that, just know you don't have to have a powerful machine to do this because the reasoning is going to be happening by default in our cloud. I mean, what we do for government and for commercial users, I mean, sometimes that's what they want. Other times they want to run it all in-house. And then you can install the reasoning server. It's all containerized. So it uses what's called Kubernetes for container orchestration. So you can install that in your own, you can install it locally on your own machine. You can also install it in your own cloud if you want to. but that's not by default. By default, community version is in our cloud infrastructure. But in terms of licenses, I mean, that's really up to you. You know, I mean, you can use Imandra for open source stuff. It could be closed source. It's fine with us.
Okay, excellent. Thank you. That answers my question. Folks, other questions? Matthew is the person who has late night time zone. So Matthew, do you want to fire if you have a question?
Yeah, sure. Thank you. That was a great talk, and it looks like a super cool system. I guess I've been doing a lot of. I'm new to the area of neural networks, which is one of the key focuses of the topic. But one of the key techniques in terms of neural networks is that they are massive, and a lot of the techniques that are coming out are incomplete. So you know they maybe sound if it. You know, you want to verify some property of your neural network, it's going to give you an answer. If it says yes, your property holds, you're definitely sure it's going to hold. If it says no, you're not entirely sure. You know, it may hold or it may not hold. But all you know is you can't prove it. I mean, I guess it's this idea of, it's kind of like bounded verification, right? But does Imandra have support for these sort of other support apart from bound verification for, you know, incomplete decision procedures?
Great question. Yes. So maybe two things I'll latch onto there. So one is for dealing, you know, scaling to systems that are massive. There's a lot in Imandra because I mean the systems we deal with in finance are just crazy, and in terms of complexity. And so we put a lot of work into modular verification. So basically. I mean, in a sense, we saw this in a very lightweight way with that reverse example. That often what you want to do is, you know, break your system into components. And in Imandra, the sort of the first step of doing that is putting functionality in different functions, like actual different function definitions. And then typically what we'll do is, if we have a very complex function, especially if it's recursive, often what we will do is we will prove the key properties we care about for that function. And then we will do what we call disabling it. And basically what that means, and actually, do I still have this autonomous vehicle one up? No, but you'll see that in that autonomous vehicle example if you look. But if you disable a function in Imandra, basically what that says is, as Imandra goes to reason about this, we're no longer going to expand its definition. All we're going to do is use the lemmas you've proved about it. So in a sense, you set up a reasoning API. You prove the properties you care about for that function, then you disable it, that makes it opaque, and all we have about it is what you proved about it. So that's not totally true. There are more nuances because we basically only use what you told us about it for proving theorems, especially by induction. But if we then want to get counterexamples, we actually want to validate those counterexamples using the full definition to make sure they're not spurious. So we do actually still go into the disabled definition to validate counterexamples, but that's typically just very efficient execution. That's not search in a sense. So that's the first thing I would say is, you know, you can modularize. You also, we have support for OCaml's module system. So in addition to disabling functions, you can wrap things up in modules and just export what you care about for those. And there's a lot of stuff to help you automate that process. So actually a new feature that we're releasing right now is an Abstractor, sort of dual to our region decomposition stuff, where you just give Imandra your executable system, you give it some predicates you care about, and Imandra will go and construct a faithful abstract model of your system that's actually finite state, where the states are determined by Boolean combinations of those predicates. And you can then reason about that. So you have a lot of freedom in creating these different abstractions built on the concrete model. So, okay, so those, yeah, there's a lot you can do for modularity and abstraction. And then the other side of your question, which is, you know, incomplete stuff and bounded verification. So that's definitely a big part of our philosophy. And, you know, you by default in Imandra, if you just say verify, you'll get a bounded, maybe if I jump back here, you know, let's do something like yeah, and actually let me use this as a nice way to show you something. So these counterexamples and things, these can involve higher order functions too. So for instance, we could ask Imandra, is it always the case that mapping F, over a list is, I'm again doing something totally silly, but is not equal to 1, 2, 3. And here this is a conjecture also involving a functional parameter and using a higher order function, and it's actually polymorphic here. And so here we had to synthesize a type, and we synthesized a function, and we synthesized a list. And so, this whole paradigm also works for higher order things, which can also be very useful for modularity, I'll say. But when it comes to bounded verification, so, let's say we did something, what would be a good example? Okay, fine X, I'm just doing something totally silly, but okay. Yeah. Cool. What did I do? Oops. Doing things live. List.map fun. I said, let's say that implies that list.map fun x greater than 0 x's. Okay. List. This is it. Oh, of course. Sorry. I meant to say for all, not map. Good test of error messages. Okay. So here, for example, this is conjecture that, I think should be true. And we're doing it over, arbitrary linked lists. So, just think this could be analogous to, neural network or some controller that's working over some arbitrary length collection of sensor readings or whatever. And, by default, we're going to do bounded verification. But as I was mentioning before, you can actually, first of all, put an explicit bound in your goal. And if you have this bound in your goal, then now this is a real result where we've said, okay, this result is true up to this bound. And you can make that precise. So that's a way, you can get a lot of mileage, especially if you have models that have these quote unquote small model properties, let's say, at least anecdotally, often if there's a counterexample, you're going to find them very quickly. And you can eliminate a lot of issues that way, and then also have a sort of discipline where you're always making sure via continuous integration or however you like to do it, that you're not introducing a change that causes one of these bounded verifications to fail. So that's a way we work very often is we start just in the bounded world. That's a way engineers who typically at a bank, for example, who don't have a verification background, they can, this is just push button. It's working over an undecidable theory, but up to a bound, it's decidable. And so, we can get out these bounded results, find lots of flaws, fix those, and, still have something that's very useful, even though it's not what we would consider full proof of correctness. And then, you can only go to, let's say, the full unbounded verification, which may involve induction if you want to. And okay, that was nice that we got that. It's like a totally random sort of conjecture. But so if this had failed and had needed some lemmas, for example, then we might have to look at it and involve some expertise. But the point is, you don't have to make that leap. First of all, you definitely shouldn't make that leap until you've verified your thing from a bounded perspective. And then finally, once you've gotten your system and conjectures to that point, then hopefully you've gained quite a bit of sort of familiarity with logic and with thinking in this way by looking through the counterexamples and how your system works and why it's correct. And you get a lot of insight from fixing the counterexamples to your conjectures and then fixing your conjectures with missing hypotheses and so on. And then you're much more prepared typically to go try and do induction, something that's unbounded. So I don't know if that long answer totally answered your question.
I think the video froze.
Oh, okay.
Right, other questions? I have a question from David Aspinall, who is not here, but I really want to give a chance for those who are present to answer.
Hi.
To answer to ask questions. Hi, Priya.
Hi. So I have a quick question about the region decomposition that you mentioned, Grant.
Sure.
Do you have a paper or anything that describes it in more detail? Just that.
Yes. You know, it's just mentioned.
Out of the press.
Yeah, it's mentioned, not in much detail, unfortunately, in our, I mean, sort of defined, but not how we compute it, in our formal verification of financial algorithms paper, which was, I think, K 2017, but we have a lot of documentation on it. So if you go, if you go region decomposition,
Okay.
yeah, and you basically, this produces Voronoi diagrams in the Jupyter notebooks, which are interactive, which is nice. But there's, sort of a thing with Imandra, we always want our results to be first class. So you also, when you do region decomp, you actually get out a data type of this decomposition that you can then compute with. And you can, translate the results into documentation. You can mine it for test cases. Actually, let me show you. So one of the big things we do in finance is we effectively mine, people write their specifications. So here, this is a DSL. So this might be something useful for you guys. This is a domain-specific language on top of Imandra for defining communication layers between systems and finance, something called the FIX protocol. That is just a pretty crazy, massive protocol that everybody uses in finance, and everybody uses it differently in incompatible ways. And so you have to translate between systems. And so this is a DSL that translates automatically into Imandra. And then we do region decomposition on it. And when we do that, oh, oops, that job is in progress. Let me show you when that's complete. When we do that, this is a very small one. I'll show you a better one that has test cases. Okay, this is what's pretty small too, but just to show you. So basically, these are now edge cases from our specification that Imandra has isolated using region decomposition. So we've taken all of the unique symbolic behaviors of this communication layer, expressed in a DSL that was then translated into Imandra. And we can go see, this is our initial state, and here are all of the different edge cases effectively that are reachable. And crucially then, we mine those edge cases, not only to go and show us what this looks like, but also we automatically generate test scripts, for example. So this is how people, one of the big uses of Imandra in finance is taking two specifications of fixed protocol endpoints, analyzing their possible behaviors, figuring out what are their unique symbolic interactions using region decomposition. And then Imandra, we mine those decomps to automatically synthesize test scripts to do testing for them that meets various regulatory requirements. And this is all building on the back of the same thing you would get out from region decomp here, available as a data type.
Yep. Okay. Thanks.
Sure.
Okay. Other questions? I will finish with a quick one. Thanks, Grant, for staying for so long, by the way, and thanks everyone for staying. But I guess you cannot cover in 1 hour the work for 10 years. So how long you work on Imandra? About 10 years? Anyway, final question from David. I just wanted to get that one is how big a role you think those visualization tools play in terms of making all this prover technology usable for people, say, in financial areas? So we think about machine learning. So how important is this whole infrastructure, which is not prover itself, but visualization, decomposition of regions, and so on, Jupyter notebooks? So where is that balance? How much of how much value you put in visualization and interface as opposed to the prover itself?
It's a great question. I mean, it's been enormously important for us. We learned that early. I mean, we learned a lot of things that sort of shocked us, especially me coming, just from beautiful world in academia of everybody recognizing how, of course, you want to prove your system correct. And, very early we learned it's very difficult to sell proofs. It's much easier to sell counterexamples. You tell someone we've verified your system's correct, or you can use our system to verify it's correct. In a bank, typically they'll say, well, we already know it's correct. And you tell them, after you slaved for a month and you finally proved it correct, well, why should we pay you for that? We knew that. Versus if you give them a counterexample, then, oh, okay, yes, I see the value. So yeah, visuals have been similar for us. First of all, in even getting them to grasp the idea of why this is different from testing, visuals have been huge. We very early on, if I show you, if you do Imandra video, we very early on, as we started, hired a motion graphics team, some good friends of ours, to create a video, basically to try to get the big ideas across. You can find if you just search Imandra video. And there, a big part of it was showing things like—
Consider the building.
Sorry, let me not put sound on, but doing, visualizations of a state space and how enormous it is. And this idea of a region decomp of, we have this infinite state space, but we can carve it up into these regions where the system has, invariant behavior, and reason about those. But there may be regions that are bad, and most regions are hopefully good. So, that just made even as we had this video, people took us much more seriously and got the idea much more easily, I think. And then, as we're more and more, we're very excited that R&D groups, for example, are using Imandra core directly, this sort of what I've been showing today. But a lot of the entryway, like the first thing Goldman did, for example, and this is all public, is they used what's called the Imandra Auditor, which is a whole visual interface powered by Imandra behind the scenes, but powered by all this automated reasoning. But it's a visual interface for basically inspecting the production system behavior, reconciling that with what a verified formal model said it should do. And if ever there's discrepancies, allowing them to step through them and then get an explanation in terms of the region that those discrepancies correspond to, driven by the formal model. And, that's very much outside of, I would say, formal verification precisely, but it's powered by it. But it's something that's much more of like a business tool for somebody who doesn't know what formal verification is to still get value. So that's been really crucial. And it wasn't until we were able to get people relying on it every day for stuff like that, that then the R&D groups started to buy in and say, oh, we want to use the underlying engine and build our own tools with it.
Okay. Yeah, cool. Thanks. We're not quite trying to make any market entry for a company, but we have a similar problem of trying to build a system usable for AI people, or maybe even lawyers and so on, for wider public who could somehow access the verification benefits.
Awesome.
So
Yeah.
we really want to learn from you about this. Yeah, good.
Well, we're constantly, constantly learning by mistake. But when you do it this long, you've made enough of them. So definitely, I would say the visuals, are very. That's great. But so, anyways, probably today's not the time because I've taken so long. But I'm very excited and interested to learn more about what you all are doing, both on the project and personally and beyond. So yeah.
Yeah, we will be in touch, definitely. We're very inspired by this all. Either we're gonna use Imandra directly, or maybe contact you with other ideas and questions that we have. Matthew has now disappeared went to bed probably, but he's the lead array here, and Wen as well, if she's around. So 2 research assistants, and Luca, the 3rd research assistant, 3 research assistants on the project will ultimately decide on the language.
Excellent.
But either way, it's either Imandra will be our big inspiration or our tool. We will see, but we will be in touch either way.
That's great. And one thing I would add too is, regardless of what your main language is, you can also just use Imandra as a backend to, find counterexamples, translate your source language like DSLs. A lot of people are building now on top of Imandra.
Okay.
So also just keep in mind, and we can help you do that. But it's easy to use Imandra as a library, and you can think about it in that sense as sort of next generation SMT. SMT lifted to be higher order with recursive functions with induction, but with counterexamples too. So you don't have to use it for everything. You could just use it for something if you want.
Well, that's actually an excellent way to think about it, because Wen and Matthew are looking into integration of SMT solvers in Agda, for example.
Nice.
And then but we've never thought of Imandra being instead of an SMT solver integrated into a language like Agda, and that's an interesting way to think about it. So
yeah, I mean, in some ways it's more direct because you can directly, an Agda data type will map in general to an Imandra data type. An Agda recursive function would map to an Imandra recursive function, especially in Agda where things are typically higher order. Then there's various ways also through Imandra to then use SMT if there's a particular, basically you can write Imandra plugins that get installed in the Imandra reasoning backend that then could connect to an SMT solver, but using all of Imandra's definitional machinery, which allows you to automatically go from recursive higher order functions to things that are first order if you want to. So anyway, so
that's a great idea. That's a great idea.
It might be useful for me as well, actually, because I was just saying, because with my planning stuff, it's like one of the bottlenecks we have is that like we've proven all like the theory of like our system in Agda, but then Agda's kind of slow when it comes to actually proving like an individual plan, just because of the way it is. And if I did the actual proving of the individual plans in Imandra, it might be a lot faster. There's potential.
Yeah, super interesting. Well, anyways, keep me posted, and we have a Discord.
Yes, we definitely should maybe arrange a follow-up meeting sometime early in the next year, maybe.
Excellent.
Right. Okay. Well, thanks again, Grant, for coming, and thanks everyone for staying so longer than an hour, much longer, in fact. Yeah, it was good to see you all.
Nice to meet you all. Bye.
Cheers. Bye-bye.
Thanks.